Okay, June 19, paper 4, variant 3. Yeah. Question 1. Figure 1.1 shows a distance time graph. Distance time graph from P all the way to V. Describe the motion between Q and R. Between Q and R. What's happening between Q and R? You have a straight line, a straight slope. So what does this motion indicate? That he's moving with a constant speed. Constant. Between R and S. So R and S is slightly bending. It's slightly bending. So this means that he is slowing down or that there is some sort of deceleration. Okay. Between S and T, the slope is zero. This means that he is at rest. This is a distance time graph. It's not a speed time graph. Okay, so he's at rest. Calculate the speed between U and V. Between U and V, how can I find the speed? How can I find the speed? I need to find V, the slope. So 600, 400, and this is 440, and 300. So basically y2 minus y1 over x2 minus x1, 600 minus 440 over 400 minus 300. Y2 minus y1 over x2 minus x1. This will give you a speed of 1.6 meters per second. Meters per second. يلا. After point V, the straight line continues down a steep hill. The cyclist travels down the steep hill. He does not apply the brakes. All resistive forces can be ignored. Again, after point V, the straight road continues down a steep hill. The cyclist travels down the steep hill. He does not apply. All resistive forces can be ignored. Sketch a possible motion for the cyclist after V. So after V, what's happening? What's happening after V? Is he moving? Think about this. So he's moving down the hill. Will I will I sketch the graph, for example, will I sketch the graph downwards? Will I draw from 600 to 0, for example? Will the graph move downwards? Definitely not. Why? Because downwards means that he's moving backwards, which is wrong. No. How will I draw the graph? So he's moving down this. So he's moving with a constant speed. Would that be correct? Again, no. He will not be moving with a constant speed. Why? Because he said there are no resistive forces. All resistive forces can be ignored. So, for example, there is no air. He's falling straight downwards. So what's happening to speed? Speed is increasing. How can I draw an increasing speed? Curving upwards. Curving, upwards. So whatever curve, you need to just draw an upward curve from V, indicating that his speed is increasing. Indicating that his speed is increasing. Okay. Question 2 is the top view of a small ship, mass 1.2 times 10 to the power of 6 kilograms, is slowly sideways. Okay, it's moving slowly sideways at a speed of 0.4 meters per second as it comes to dock. This is the motion. Calculate the kinetic energy before it hits the pillars. Kinetic energy equals half mv squared. So half times 1.2 times 10 to the power of 6 times 0.04 squared. 1.2 times 0.04 squared. This will give you a kinetic energy of 960, around 960 joules. It's moving very slowly. The ship is in contact with the pillars for 0.3 seconds as it comes to rest. So it hits the pillars, it comes contact with the pillars for 0.3 seconds. Can I find the force applied on the ship? Yes, I can find the force. You can use one of two equations. Either you can say force equals mass times acceleration and you need to find the deceleration, v minus c over t, or you can use the impulse equation, which is force times time equals mv minus mu, which is again the same equation. We might say mu or mv is zero, so you have the time, you have the mass, you have the velocity. Basically, force would be equal to mv over t. So the mass, which is 1.2 times 10 to the power of 6 times the velocity, which was 0.04 over the time, which is 0.3. This would give you a force of 1.6 times 10 to the power of 5. Around 1.6 times 10 to the power of 5 newtons. Okay? Yeah. Assume the kinetic energy is used to do work moving the pillars. Moving the pillars. So we'll say that the pillars will move for some distance. Calculate the distance moved by the pillars. Calculate the distance moved by the pillars. Hmm. How can I find the work? Well, what is the equation? Work done equals equals force times distance moved. Do I have the work done? Yes, I have the work done, which is the kinetic energy. 1.6, okay, 1.6 times 10 to the power of 5. Do I have the force? Yes, I do have the force. 960. I'm sorry, I switched them. You have the kinetic energy, which is 960, and you have the force, which is 1.6. Okay, kinetic energy, which is 960, and you have the force, which is 1.6 times 10 to the power of 5, multiplied by the distance. All you need to do is divide, okay? Divide the work done, 1.6 times 10 to the power of 5, which would give you a very, very small distance. Definitely, indeed, it's a very small distance. It's around 0.006 meters. 0.006 meters or zero point 0.6 centimeters, a very small distance. You're not moving the whole dock, you're just slightly moving the pillars, a very small distance, only 6 millimeters. Only 6 millimeters. The dock walls sometimes have the pillars replaced with rubber car tires. Okay, sometimes you replace these pillars with rubber car tire. Explain how this reduces the possibility of damage when a boat docks. It definitely doesn't, it's not a possibility. It definitely reduces the damage when a boat docks. Why? When you add these tires, what happens to these tires? They get compressed when the boat hits them. They get a bit compressed. Why? Why do they get compressed? Or how does this compression help with not damaging or reduce the damaging cost caused on the boat? By increasing the time. If you think about the impulse, now you need to stop the boat completely. You need to stop them. So impulse equals force times time. During this compression, during the compression of the tires, the time increases and therefore the force decreases. As you increase the time of collision, okay, as the time of collision increases due to the compression, okay, you could say due to the compression. The force decreases. The force on the boat decreases. That's it. It's impulse. If you increase the time, you decrease the force. Figure 3.1 shows a small submarine submerged below the surface of the sea. The density, calculate the pressure, okay? When the submarine is 3 times 10 to the power of 3 meters below the surface of the sea. That's a huge distance. Can I find the pressure? due to the seawater alone, yes, I can find the pressure due to the seawater alone. And even if you add the total pressure, even if you add the atmospheric pressure in this question, it wouldn't really matter that much. Why? Because it's already at a distance of 3,000 meters. 3,000 meters below the surface of the sea, that would give you a huge pressure, an extremely huge pressure. I guess it would be something in the megapascals, I guess. Let's calculate it. Okay, so pressure equals rho gh. The density is 1030 times the g 9.8 times the height or the depth 3 times 10 to the power 3000 meters. That's a lot. That is a lot. Times 9.8 times 3 times 10 to the power times 10 to the power of 3, which is 30 million. Yes, I was right. 30 million, which is 3 times 10 to the power of 7 pascals, or 30 megapascals. Okay, 3 times 10 to the power of 7 pascals. I even uh, removed the 200,000 pascals, which is insignificant. So even if you add the atmospheric pressure to this question, which is only 100,000 pascals, it's nothing. Again, it is nothing. The submarine emits a pulse of sound to detect other objects in the sea. The speed of the sound in the seawater is 1,500. The echo received with a time delay of zero point 0.5 seconds after the original sound is emitted. So basically, this is an echo. Can I find the distance? If I'm talking about an echo, the speed would be equal to 2 distance over time. Why? Because the wave hits or goes all the way to the object, hits and reflects back. To find the distance, it would be speed times time over 2. 1,500 times the time, which is zero point 0.5 over 2, will give you a distance of 375 meters. Another pulse of sound is emitted through the air when the submarine is on the surface and echo is received. The echo is received after zero point 0.5 seconds. Compare the distance of the second object with the distance calculated in BI. Okay, that would be easy. The sound in air, is it the same value? Is the speed of the sound in air the same value as the speed of the sound in water? Definitely not. The speed of the sound in air is much less, which is around 340 meters per second, and you're required to know this. It's in the range of 330 to 350 meters per second. So if you say 340 meters per second in the air, and you find the distance with the same time, so 340 times 0.5 over 2. Would it be it would definitely be a smaller distance. Why? Why would it be a smaller distance? Because the speed in air is much less. That was easy. Okay, moving on. Question 4. Water molecules escape to the atmosphere from a boiling pan. State 2 ways in which boiling is different from evaporation. I guess we have memorized these answers. The difference between the boiling and the evaporation. Boiling happens throughout the whole liquid. Boiling happens throughout the whole liquid. The whole liquid, while evaporation hmm, happens only on the surface. On the surface. Okay. What is another difference is that boiling happens only at a specific temperature. Boiling happens at a specific temperature, while evaporation happens at any temperature. Evaporation can definitely happen at any temperature. Figure 4.1 shows a heater in a metal block. You have a heater, you have a metal block. The power of the heater is 370 watts. It's switched on for 4 minutes, so you can find the energy, the specific heat capacity, the mass, calculate the increase in energy. increase in temperature, I'm sorry. Can I find the increase in temperature? Yes, energy equals mc delta T. Can I find the energy? Yes, energy equals power times time. So instead of saying E equals mc delta T to find the energy, I need to find power times time equals mc delta T. The power would be 370, the time is 4 minutes, but you need to convert these minutes into seconds by multiplying by 60. You have the mass, which is 5 kilograms, and the specific heat capacity, which is 420 kilograms, times delta T. To find delta T, this would be 370 times 4 times 60 divided by 5 times 420. Yeah. This would give you a delta temperature, a change in the temperature of around 42 degrees Celsius. 42 degrees Celsius. Again, 4 marks is a lot. That's why we had a lot of steps in this question. Question 5. A cross section of the inside of a vacuum flask. The vacuum flask is being used to keep a liquid cool. To keep a liquid cool on a hot day. Explain how the labeled features help keep this liquid cool for a longer time. We need to include all of the processes involved. So we have glass, we have a vacuum, silvered surfaces, we have a stopper. So let's talk about them one by one. For example, the stopper. What does the stopper do? Okay, what does the stopper do? It stops the stopper. What does it stop, or what does it prevent, or what does it reduce? So the stopper, it reduces the heat lost by what? Reduces the heat loss by convection. Kind of prevents convection, prevents the hot air from rising up or cold air falling in or whatever. So it reduces the heat lost by convection. Or actually the heat gained. This is not heat lost, I'm sorry. Heat gained. Why? Because this is cool liquids. Heat gained by convection. Ah, what about the silvered surfaces? Okay, silvered surfaces. What do they do? Silver, shiny white is the. Is it the best or the worst? Is it the best or the worst? Hmm. They are the worst. But in this case, are they the worst absorbers or the worst emitters? Think about it. This is a cool liquid. Hmm. Worst absorbers. Yes, absorbers. Hmm. Of infrared radiation. Of infrared radiation. So they keep the liquid cooler for a longer time. They wouldn't absorb as much heat or as much infrared radiation. Yes, excellent. What about the vacuum? This is very important actually. The vacuum. Hmm. Why is the vacuum important? Because it totally prevents, okay? It prevents heat lost or heat gained in this case by two things, by conduction and convection. Conduction and convection. It cannot prevent heat gained by radiation. Nothing can stop radiation, but the vacuum can prevent the heat gained by the conduction and convection. Last but not least, the glass. What does the glass do? Well, the glass is a poor conductor of heat. It's a poor conductor of heat. So it reduces the poor conductor of heat, reduces the heat gained. Hmm. Heat gained by what? By conduction. 5 very well deserved marks. Suggest a suitable material for the stopper. So I have the stopper, I have the lid. What would a suitable material for this lid be? Definitely any non metal, any insulator. Any insulator. I've seen a lot of people actually. Um, yes, you can write down cork. It would be correct. You can write down wood, plastic. Yeah, all of them are correct. Okay, so wood, cork, plastic, whatever. Okay. Glass. Figure 6.1 shows wavefronts of a wave approaching a narrow gap and passing through this gap. The wavelength is lambda. State the name process. What is this process called? It's called a diffraction. Yes. A wave of wavelength lambda over 2, so half of the original wavelength, approaches the same gap. Okay, we need to draw three wave fronts for this wave as it approaches the gap, and three wave fronts after they pass through the gap. How can I draw them? So initially we need to measure the wavelength, measure this wavelength, and draw three wave fronts which are much closer, actually at an exact distance of lambda over 2. You need to measure it very carefully and make sure they are exactly lambda over 2. Exactly, the distance between them is half the wave length, half the original wavelength. They're moving this direction, okay, with half the wavelength. Again, you need to be very accurate while drawing these wave fronts. After they, or as they pass through the gap, this gap would be kind of wide. This gap would be wide. So as you draw these wave fronts passing through this gap, would they diffract as much? Would they diffract as much? No, definitely they would not diffract as much. This would be a wide gap. So we kind of would draw straight waves. Okay, you draw straight waves with the same wavelength, with the same wavelength, and then they're just curved at the end. Curved at them. Again, you're drawing these waves using a ruler, okay, with distances, with equal distances. Equal distances. You have to draw equal distances, which are half the original wavelength, okay? And then they are curved at the ends. That's it. Equal distances, which are curved at the ends. That's all you need to draw. Okay? Okay. Table 6.1 shows 5 different types of electromagnetic waves. In the blank column, write the numbers 1 through 5 to show the order of wavelength. 1 for the shortest wavelength and 5 for the longest wavelength. Shortest is 1. Shortest wavelength is 1, which is the highest frequency. So gamma has the highest frequency, so this would be 1. Shortest wavelength. And then, after gamma, if you write them down, Rami, looks great. Gamma rays and then X rays. So you have X rays. Then you have ultraviolet. And then you have light and then microwaves. State the speed of radio waves in air. 3 times 10 to the power of 8 meters per second. A radio station transmits radio waves with a frequency of 96 megahertz. Mega means times 10 to the power of 6. Can I find the wavelength? Yes, I can find the wavelength. Wavelength equals speed over frequency. So 3 times 10 to the power of 8 over the frequency, which is 96 times 10 to the power of 6. Should give you a wavelength of 3.1 meters. Radio waves have a long wavelength. Yes, 3.1 meters. It is acceptable, definitely. Okay. Hmm. Moving on to question 7. 7.1 shows light approaching a boundary between the two materials at a speed of v. After crossing the boundary, the speed is 1.3 v. Think about it very carefully. Initially, light was traveling at a speed of v. After crossing the boundary, the speed was 1.3 v. This means that the speed has increased. Just put it into consideration. The speed has increased. Okay, what is the angle of incidence now? Angle of incidence, is it 50? Definitely not. It's not 50. You have to draw the normal, okay, and say that the angle of incidence is 90 minus 50, which is 40 degrees. This is the first part of the question. The angle is 40 degrees. Can I find the angle of refraction, which might be a bit tricky? To find the angle of refraction, you need to find the refractive index. You need to find the refractive. How can I find the refractive index? It would be the speed of air, the speed of light in air, over the speed of the light in the medium. Which of these speeds is the speed of light in the air? Is it v or 1.3 v? Which of these speeds is the speed of the light in the air? If you think about it very carefully, you'd find that the speed of the light in the air would be the 1.3 v. Why would this be the speed of the light in the air? Because you cannot have a speed greater than the speed in the air. So if you say, for example, that the speed of the light in the air, which is v, if you say that this is the speed of the light in the air, which is 3 times 10 to the power of 8. So saying that 1.3 times 3 times 10 to the power of 8, this would give you a number much larger than 3 times 10 to the power of 8. I guess it would be around 4 times 10 to the power of 8. Is there any speed that could reach, is it even possible to reach this speed? No, it's not possible. So it cannot be. The speed of light in the air has to be the 1.3 v. So if I write it down as 1.3 v, this is the speed of light in air over the speed, whatever v, the speed of light in the medium. Can I find the refractive index? Yes, I can find the refractive. So 1.3 v over v, so you can't cancel out the v's. So the refractive index would be 1.3. Now, can I find the angle of refraction? Yes, I can find the angle of refraction. I have the equation n equals sine theta air over sine theta medium. Again, theta medium. Think about it carefully. This light was moving between two materials. After crossing the boundary, so after it crosses the boundary, it goes into the air. So initially it was in the medium. Initially it was in the medium. So this 40, this angle of incidence, this is the theta m. This is the theta m. This is the theta inside the medium. It's inside the medium. So basically, you have the theta m, you have the n, and you need to find sine theta a. How can I find theta a? Theta a would be equal to sine inverse n times sine theta m, which is 1.3 times sine 40. Sine inverse 1.3 times sine 40, which would be around 57 degrees. 57 degrees. Yeah. Okay, figure 8.1 shows a 240 mains supply connected to an air conditioning unit and a freezer. A fuse X is placed in the circuit as shown. The freezer has an operating power of 700 watts. 700. Calculate the current in the freezer. So power equals VI, or I equals power over V. Since they are both in series, so the power 700 and the voltage would be 240. 240. The current would be around 2.9 amperes. And this is easy. The current is 2.9 amperes. The maximum operating current of the air conditioning unit is 7.5 amperes. So the current would be 7.5 amperes. And the current in the freezer would be 2.9 amperes. Fuses of current ratings 1, 3, 5, 10, 13, and 30 are available. Suggest a suitable rating for X. Give 2 reasons for your answer. So the total current in the circuit now would be 7.5 plus 2.9. 7.5 plus 2.9, which is 10.4. The total current is what is 10.4 amperes. This is the total current in this circuit. A suitable fuse rating would be 13. A suitable would be 13 amperes. Why is that so? Why is that so? First of all, first of all, you need to say that any fuse of the other fuses, 1 and 3 and 5, would be less than 13, would be less than 10.4, and therefore they would instantly melt. Okay, you have to write it down as how did we 2.9 plus 7.4 is 10.4. 7.5, I'm sorry, is 10.4. Any other fuse of 1 ampere, 3 amperes, 5 amperes, and 10 amperes uh, would instantly melt. Okay, they would all melt. Another reason why didn't I choose the 30 ampere fuse? It is too high. Okay, the components would be damaged before the fuse. 30 ampere fuse is too high. The components would be damaged before it melts. Okay. Okay. A fuse is made out of a short length of wire. Explain why fuses of a higher rating are made of a thicker wire. Why, for example, the 30 ampere fuse? Why would it be much thicker than the 10 ampere fuse or the 1 ampere fuse? Hmm. If you think about it, as the current increases, what happens to the fuse? The fuse melts. Okay, so the fuse melts because the heating effect, okay, the heating effect is increases because the fuse. So you say that as the current increases, the fuse melts. You can state the equation, which is power, but not power equals IV. Power equals I squared R. Why? Because we need to relate the resistance. We need to relate the resistance as thicker wire. As the diameter increases, what happens to the resistance? You could say that the resistance decreases. Decreases. So if you have a very thin diameter, the resistance would be too high and it would melt instantly. Melt instantly. Why? Because the heating effect is directly proportional or is affected too much by the thickness. Okay. You can say, for example, that the as diameter increases, resistance decreases, and the heating effect decreases as well. And the heating effect also decreases. Electrical energy can be obtained from renewable and non-renewable sources of energy. State two renewable sources of energy. Any two renewable sources of energy. For example, solar, hydroelectric. The hydroelectric, solar. Huh. State one social, economic, or environmental disadvantage of one of your answers to DI. Huh. Social, economical. For example, the hydroelectric. One environmental disadvantage of the hydroelectric is it causes flooding. So the hydroelectric causes flooding behind the dam. behind the dam, and for example, destroys the animal habitat and destroys the animal habitat. Okay. Hmm. We have an electrical component. What is this electrical component called? It is an LDR, or a light dependent resistor. Light dependent resistor, or an LDR. Definitely B is cancelled. You're not required to draw NOR gates. C is cancelled. Okay, this whole page is cancelled. Not this whole page. Actually, we can solve D, referring to a simple electron model. State why what distinguishes electrical conductors from insulators. This is easy. Conductors have mm, free moving electrons, while insulators do not. Okay, that was easy. Question 10. Figure 10.1 shows a simple alternating current generator. You have the rotation of the coil in this direction. You have magnet. Okay, and the output on figure 10.1 sketch of graph to show the how the electromotive force induced varies with time for one revolution. Assume that the coil starts in the horizontal position as shown in 10.1. So it starts off with this position. It starts off with this position, this horizontal position. It needs to complete one full cycle. We'll draw one full cycle. So most of you would say, well, let's draw a sinusoidal wave. Let's draw a sinusoidal wave. Um, would that be correct? Well, we need to think about it. In this position, would it give off the maximum output, or would it give off the minimum output? Hmm. This is the horizontal position. So instantly, okay, and this instant, it's kind of moving upwards from this side and kind of moving downwards from this side, right? At this instant exactly, it's kind of moving upwards from this side and downwards from this side until it starts to rotate, right? So at this instant, when it's moving upwards or downwards, it's cutting the field, it's cutting the magnetic field perpendicularly. When it cuts the field perpendicularly, it gives off the maximum output. It gives off what? Gives off the maximum output. So at this position, the horizontal position, it's giving off the maximum position. So you need maximum output. So you need to draw, or you need to start the graph with the maximum position. You will not draw a sine wave. You'll actually be drawing a cosine wave. A cosine wave, which starts off from 1, or the maximum, goes to 0, and then reaches the minimum, and then back to the maximum. You have to draw a cosine wave. This is a full wave, 360 degrees. Label the points where it has completed quarter of a revolution and 3/4 of a revolution. So this is at the start of the rotation, 0 degrees. It hasn't completed yet anything. At this position, it's half of the revolution, only half of the wave. So quarter of the wave would be at this position. This is quarter of the wave, and this would be 3/4 of the wave. Why? Because this is the complete wave. So 1/4, 2/4, which is half, then 3/4, or 3/4 of the wave. Explain why EMF is induced only when the coil is turning. So if the coil stops, would there be any induced current or any induced EMF? Definitely not. Why does it only induce current or EMF when it's rotating? Because it's continuously cutting. You have to say cutting, okay? It's continuously cutting the coil. So cutting sorry, cutting the magnetic field, cutting the magnetic field hmm, induces EMF and current. State the name of the components P and Q and state their purpose. What are P and Q? P and Q. What are they? Are they split ring commutators? No. This is an AC generator, so they are slip rings. They are slip rings. They provide a continuous connection. They provide a continuous connection. Slip huh, rings. They are connected, okay, to the coil continuously while rotating. State two possible changes that cause a larger EMF to be induced. How can I huh, induce a larger EMF? You have three reasons actually, three of them, which are increasing the speed of the rotation, increasing the magnetic field, increasing the number of turns. Increased speed of rotation, increase the strength of the magnetic field, yeah, of the magnetic field, or increase the number of turns in the coil. Hmm. Americium is a radioactive isotope. A nucleus contains 95 146 neutrons. It decays by emitting an alpha particle. Write down the nuclide equation. Okay, so americium, Am, it has 95 protons and neutrons. So what is the total nuclear number? 241. 241. It decays by producing Neptunian. Let's write it down this way. Np and alpha. But alpha is 4 and 2. We know that alpha is 4 and 2. What about Neptunium? It has to be 93. And the the nuclear number would be 237. So 4 plus 237 is 241. 2 plus 93 is 95. Ionization. Smoke detectors contain americium and two small electrodes with small voltage between them. The air between the electrodes is ionized by alpha particles so that there is a small electric current between the electrodes. The air is ionized and the electrodes conduct electricity, so it's fully operating. Suggest and explain the effect of the smoke on the current between the electrodes in the smoke detector. If there is a lot of smoke, okay, there is a lot of smoke. What happens to the current? Hmm. Yes, the current decreases. Okay, the current stops. Current stops. Why does the current stop? Basically, because the air is now, or originally the air was ionized. If you increase the amount of smoke, if you increase the amount of smoke in the air or between these electrodes, okay, so all of the smoke will absorb the alpha particles. The smoke absorbs the alpha particles. So you cannot ionize the air anymore. You cannot ionize the air anymore. So you can only ionize the air if there is no smoke in this air. Therefore, the current will not pass, the air will not be ionized, and the electrodes won't conduct any electricity. Suggest two reasons for using an alpha particle emitter in a smoke detector. Why would we use alpha particles instead of, for example, let's say gamma or beta particles? First of all, because of the ionization effect. This is the most important part. Because of the ionization effect. And second of all, okay, you can say that the alpha particles are safer. Okay, they are safer because the distance that they travel is very short. Okay, First and the most important reason is that alpha is highly ionizing, hmm, ionizing. And also alpha is safer since it doesn't travel large distances. Okay? Okay.